Welcome, everyone. Today, we are going to conduct a deep dive into one of the most powerful quantitative tools in a manager's entire arsenal, linear programming. Now, I want you to think about this. At the very heart of every single business, I don't care if it's a tiny startup or a massive Fortune 500 company, there is a constant, unavoidable challenge. How do you make the absolute best, most profitable decisions when you're operating in a world with fierce competition and, more importantly, limited resources? This isn't just some academic exercise. This is the day-to-day reality of management. So today, we're going to explore the mathematical framework that's designed to bring real scientific rigor to these critical choices.
So let's really frame our central problem with this question. How does a business make the perfect choice? And I want you to pay close attention to that word. We are not talking about a good enough choice or a decision that's based on a gut feeling or past experience. We are hunting for the single best, mathematically provable course of action. Just think about the decisions managers are wrestling with all the time. Given our factory's capacity, should we produce 10,000 units of product A and 5,000 of product B? Or is the optimal mix actually 8,000 and 7,000? Or, given a marketing budget of, say, $2 million, what is the precise allocation across digital, print, and television that will absolutely maximize our reach? How should a logistics company route its entire fleet of trucks to meet all its delivery deadlines while minimizing its total fuel bill? You see, just relying on intuition in these incredibly complex scenarios isn't just risky, it is a direct path to giving up your competitive advantage. What we need, what you will need, is a systematic method for navigating all this complexity.
Okay, let's get into it. The formal academic name for this whole hunt for the perfect choice is optimization. At its core, optimization is just the process of finding the best possible outcome from a given set of options, all while operating within a very specific set of rules or limitations. The goal? Well, it can be to maximize something you want, like profit, market share, or production output, or, on the other side of the coin, to minimize something you don't want, like cost, waste, or employee turnover. I want you to understand this. Every single strategic decision you will make in your business careers can, in some way, be framed as an optimization problem. Grasping this concept is fundamental to moving from just running a business to strategically leading one. Now, what's so powerful about this is that it's a universal truth. These limits, which from here on out we're going to formally call constraints, are the non-negotiable realities of the business world. So let's make this really tangible. Time isn't just a concept. For a manufacturing plant, it might be 800 available labor hours per week. That's a hard ceiling, dictated by union contracts and overtime laws. Budget isn't just some number on a spreadsheet. It's a marketing department's $1 million quarterly allocation, a figure they absolutely cannot exceed without getting approval from way up the chain. And materials, well, that represents a finite supply of silicon wafers for a chip manufacturer or a limited amount of high-grade coffee beans for a cafe. These are not suggestions, right? They are the real, tangible boundaries that define what is even possible. They create the very problem that optimization sets out to solve. So, if we have a clearly defined goal, optimization, and we've identified our non-negotiable limits, our constraints, how do we systematically connect those two things to find the single best solution? Well, this is where we introduce our main tool for today's lecture, linear programming, or LP for short. Think of it as a powerful mathematical framework that lets us take a messy, real-world business problem and model it with incredible precision, which then allows us to calculate the optimal solution. It's the bridge that takes us from strategic goals to actual operational execution. Let's move on and see exactly how this is built. So here's the textbook definition, and I really want to unpack this carefully. Linear programming is a mathematical method. What does that mean? It means its results are objective, they're repeatable, and they are provable. They're not based on opinion. It's used to solve optimization problems to find the best outcome. Now, the single most important word on this slide, the one that gives this whole technique its name, is linear. You see, LP operates on a critical assumption that the relationships between our variables are linear. This means two things, proportionality and additivity. Proportionality means that if producing 1 unit of a product requires, say, 2 hours of labor, then producing 10 units requires exactly 20 hours. There are no economies of scale or setup costs in a basic linear model. Additivity just means the total of all activities equals the sum of the individual activities. Now, why is this so critical? Because this assumption of linearity allows us to model the world with straight lines and flat planes, which creates problems that computers can solve very, very efficiently. If these relationships were nonlinear, we'd be in a much more complex world, needing far more advanced math. A key skill for you as a future analyst is learning to spot when a business problem can be reasonably approximated by a linear model. Okay, to build a valid LP model, we need two key components. First, the objective function. This is a single linear mathematical equation that states your goal. So for instance, if you make a $50 profit on each unit of product X and a $60 profit on product Y, your objective function to maximize total profit would look like this. Profit equals 50 times X plus 60 times Y. This is the metric you're trying to push to its highest possible value. Simple enough, right? Second, we have our linear constraints. These are linear inequalities that represent our limits. Let's stick with our example. If product X takes 2 hours of labor and product Y takes 3 hours, and you have a maximum of 120 labor hours available, your constraint is written as 2x plus 3y is less than or equal to 120, and you'll have one of these for every single limited resource you have. Now, here is a very common mistake students make, so please listen closely. They often forget the non-negativity constraints. X must be greater than or equal to 0, and Y must be greater than or equal to 0. It sounds obvious, but without those, the model might tell you the optimal solution is to produce negative 50 chairs, which is physically impossible. The key here is that we combine that one objective function with all of the constraints to create a complete mathematical model that precisely mirrors our business problem. All right, let's pivot from the theory for a minute and talk about where you're actually going to see this in action. The applications of linear programming are absolutely vast, and they're deeply embedded in the operations of pretty much every modern enterprise. Seriously, this isn't just a topic for your exam. This is one of the most widely used and financially impactful quantitative techniques in the business world today. It's often running silently deep inside the supply chain and financial software that powers global commerce. And this slide here brilliantly illustrates just a few of the core applications. When we talk about optimizing production schedules, we're really talking about the classic product mix problem. I want you to imagine you're a manager at a company like Procter & Gamble. You have finite resources, machine time, labor, raw materials, spread across multiple product lines like Tide, Crest, and Pampers. Linear programming is the tool that determines the exact production quantity of each one of those to maximize the overall corporate profit. For allocating resources efficiently, think about an airline like Delta. They use massive, and I mean massive LP models to schedule thousands of pilots and flight crews across tens of thousands of flights. The goal is to minimize costs while adhering to this complex web of constraints like FAA regulations, union work rules, and making sure crews are in the right cities for their next flight. And maximizing profits isn't just about production. In finance, this is called portfolio optimization. An investment firm will use LP to build a portfolio from hundreds of possible stocks and bonds to maximize the expected return, subject to constraints on the portfolio's overall risk level and diversification rules. So as we start to wrap up our deep dive, what is the single most important idea that I want you to take away from our discussion of linear programming today? Well, it's really about the transformation of messy, qualitative business problems into clear, solvable mathematical structures. It is about replacing the phrase, "I think we should do this," with "the data shows the optimal solution is this." You see, the true power of linear programming is its ability to take a complex, real-world business scenario with all of its competing priorities and its various limitations and translate that whole mess into a structured, solvable math problem. It actually forces a manager to explicitly define their objective and to quantify their constraints, which is an incredibly valuable exercise all by itself. It strips away the ambiguity and it provides a path forward that isn't just a good idea. It is demonstrably the best possible path. And let me be perfectly clear about this. This empowers you as a decision maker to move beyond simple intuition and to justify your strategy with cold, hard data and mathematical proof. In any boardroom, in any strategic meeting, that is an incredibly persuasive and valuable skill to have. And so, I'll leave you with this final thought. It's really a challenge. This framework isn't just for multinational corporations. I want you to think about a part-time job you have, or a student club you help manage, or even just your personal study habits. You have an objective, maybe it's maximizing your income or your GPA, and you have constraints, a limited number of hours in the week, a budget, prerequisite course requirements. How would you begin to formulate that as an optimization problem? For next time, just try to write out a potential objective function and at least 2 constraints for some part of your life. Start thinking this way. What part of your world, big or small, is an optimization problem just waiting to be solved? Thank you.